Hi, my name is Marco Keltoven, and I'm an engineer, and I also do research at Worcester Polytechnic Institute on radioactivity. This small lab bench is where some of the samples that we collect for radioactive contamination get processed. And I just want to talk about a few simple ways we can improve on the way we sample and test as citizens and can get some better data to tell us more about radiation in our environment. Best piece of equipment starts with a laboratory notebook so that we're taking careful notes, keeping good records of everything that we do with our sampling. That's probably one of the key things for making sure that our data is going to be widely accepted or provable in court or maybe even publishable in a scientific journal. So what we're writing down is the place that we collect our sample, the time, the date, what we sampled, why we sampled, what we're looking for, and enough detail so that if someone has to repeat our work, they can look at your notes and they go back to the same place and get the same sample. So when you're writing down information about your samples, make sure you've answered enough of this so that somebody else could look at your notes and do the same thing. And that's really the basis of repeatability, making sure that others can prove that your work was correct. The second thing that we do is we try and take multiple measurements. Whatever we're doing for radioactivity, we'll do it 3 times. That way we'll see if whatever number we're getting is different, is changing because of random error, or it's really changing because of something that's happening with your samples. And then the last thing to keep in mind before we even start doing our testing is the idea of background. We've all heard about how radiation is everywhere. There's more radiation in a banana than in an exploded nuclear power plant. I exaggerate. But we've heard this before, and what we have to do is make sure that when we take a reading, we're taking a look at what's happening in the background too. So before we even collect our sample, if we're using something basic, like a Geiger counter, we'll take a clean working surface where there's no sample, and we'll take our first measurement. Actually, if you remember, our first set of 3 measurements. So we're going to write them all down, and that's when there's no sample at all, and we've got our background number. And then we want to take a sample, and we want to see if it's different. So I've got a few things here that we can take a look at, and we can see whether or not there's a serious difference. So I have a basic Geiger counter with a probe that's sensitive to alpha, beta, and gamma radiation. And let's turn on the audio. So now we're hearing background. This is what's happening when there's no sample on the probe. So I want to take a little item that was gifted to me by a friend from Russia, and this is a piece of the control panel from the Chernobyl power plant. This is an indicator light that tells whether or not one of the control rods is in or out. So if we take this sample, we put it on our Geiger counter, and then right away we can see that there's more radioactivity in this sample than there is in the background. So what we're really looking at is how many counts there are in a minute. And we'll take 3 measurements, same amount of time, and then compare them to 3 measurements of what's in the background and see if that difference is really significant. So now if we were to take a sample of something from your area, and after we've looked at the Chernobyl sample and we've looked at the background, we'd like to know where it falls. Is it going to be higher, lower, closer to the background? So here I have a little bit of scale. If you've heard about fracking and taking oil and petroleum fluids out of the ground by opening up underground reservoirs, when you do fracking and you pull up all this groundwater, one of the things you pull up is some of the naturally occurring radioactive material, the uranium and thorium, radium, things that are buried in the bedrock, and you bring them to the surface. And like a lot of pipes that we have in our homes, the pipes used in fracking, will get some scale. So let's take a look at the scale that we have from a gas well. We'll put that on the Geiger counter and think about what we had when we looked at the piece of the Chernobyl control panel. Well, this isn't really a video about fracking, but you get the idea. There are naturally occurring radioactive materials, in addition to fission products, cesium, that we might get from a nuclear accident. So how do we distinguish the uranium and thorium that are natural, if a little bit concentrated, from the fission products? For that we use a different kind of device. There, that's annoying. For that we actually use a gamma spectrometer. And what this does, we use a crystal, and the crystal actually will give off flashes of light when it's exposed to gamma rays. And we can actually see which isotope those gamma rays are from. So what that lets us do is find out what different compounds are going to be in our sample, what different isotopes. So if we take a look at this, let's take our naturally occurring radioactive material sample, and let's pop that right down into our gamma spectrometer. No noise this time. But what we're going to do is we're going to take a look at the different gamma rays that this gives off. So we'll start up the spectrometer. And this isn't particularly fast or exciting, but what's nice about it is you very quickly will see different gamma lines that are going to be associated with uranium, thorium, cesium. These will help tell them apart. And what we get are different parts of our graph. I don't know how easy this is to see. We'll start to see different gamma lines being recorded, and each one is going to be characteristic of the sample that we get. So what we do in the laboratory is we'll actually use a little bit of uranium, a little bit of cesium, and we'll compare and see what gamma lines we get with our instrument. Then we'll take our unknown sample, and we'll actually look at how much of each isotope is present by doing the gamma line search. Now this is a sample of vacuum cleaner bag dust. Probably one of my favorite samples to take, because vacuum cleaner bags tend to take in a lot of contaminated dust from outside that collects in the house. The vacuum cleaner bag samples they're already dry. Water tends to absorb some of the radioactive energy and makes it harder to look at. This is why it can be so difficult to look at things like whole fish or whole foods, even a banana. When it's not dried, all that material, all that bulk, all that water absorbs some of the radioactivity. We don't get a good sample. But a vacuum cleaner bag sample is nice and dry, and any hot particles that might have blown in with other dust from the environment, and hot particles are just dust that have a lot of radioactive material in them, they get trapped in that vacuum cleaner bag, and we use a sample of about 5 grams. And that's all we need to do the gamma analysis. So we'll just clear that spectrum. In it goes. That will usually run for between half an hour to overnight. And we'll look at some of the different gamma spectral lines that we get by looking at our vacuum cleaner bag dust sample. You can see there are a few things that we need to know about that right away, and I'm going to go back. Place, time, date, what the sample was, why you took it, and for a vacuum cleaner bag we're also talking about the address, maybe even the residence in the home. I'm going to write all this information down and make sure that that travels along with our sample. And to do that we use what's called a chain of custody, and I'm going to give an example. This is a chain of custody that was filled out by one of our volunteer samplers in Japan. This sample came from Sapporo, Japan, on the island of Hokkaido. And what they did is they filled in the location, the date sampled, the time it was sampled, what they sampled, who did the sampling, and they even included a nice little photograph. That's a little more than I expected. Some of the best engineers I know never bothered to do that much work on a chain of custody. And then if you're thinking this is going to be part of a legal case, make sure that you sign that right here, and make sure that that travels with your sample. Pack that sample nice, get it sent to the laboratory or to our research group at Worcester Polytechnic Institute if it's a radiation sample. And all we need is that 5-gram sample of dust, and we can start looking for any of the radioactivity that might be found in the sample. A few other things to worry about. I'm wearing gloves. You should be wearing gloves when you're doing your sampling. You never know what's in the samples that you collect, and we never know what's going to be in the next box that we open. So always make sure you take that measure of safety. The other thing that we do, sampling mask. Maybe you're sampling for radioactivity. You might even be taking a control sample, a sample from a place that you know is not contaminated. So you can use that to find your background. I love it when people can include a control sample in the set of samples that they're sending to me. They don't have to tell me which one is which. That way it doesn't introduce any biases. But even when you're taking a control, there are other things in dust that can be harmful. Besides radioactivity, you can have lead paint particles in dust. Very common problem. You might have asbestos in the dust. And if you're from the southwestern United States, you could have hantavirus or other kinds of animal or bird droppings that contain biological contaminants that might be harmful. So having a good dust mask is always a nice idea and something you need when you're doing your sampling. Remember that if you're going to open up a vacuum cleaner bag to take a sample, potentially a lot of that dust is going to be flying everywhere. I like to do that outside and not cause any further contamination in the home being sampled. You might have some of these. Paper dust mask. This one has a little valve in the front to make it easier to use. They're better than nothing, but really it's worth investing the $30 and getting one of these and getting a good dust cartridge to go with it. It doesn't take out toxic gases. If someone were to expose you to something like ammonia or some other fume, it doesn't protect you, but it does keep out the dust, and that's very important. So some really basic steps here. What we're looking for, dry samples, dusts are excellent, soils also work as long as they're dried. Good records that tell us where the sample was taken, who collected it, so someone else can go back in and take that sample. We also want to make sure that you're being safe, gloves, mask, not going into places where your own exposure might be too high, and just again, making sure we're looking at the background at the same time. We put all of these things together, even if you don't have the gamma spectrometer or you have a very basic Geiger counter, you can still take the kinds of radiation measurements that will help people understand what's happening in the environment around you. Thanks for listening.